welcome to this plenary session. My name's Stefano Baroni from Scuola Internazionale Superiore di Studi Avanzati in Trieste, and it is my pleasure and honor to chair this plenary session, this plenary lecture given by Ali Alavi from Max Planck Institute in Stuttgart and the University of Cambridge, who will tell us about the latest development of his stochastic wandering in Hilbert spaces. The title being,
So where is this? It's disappeared. Is it? Let's go back.
Okay, non-unitary and stochastic quantum chemistry. You have 40 minutes.
Thank you, Stefano. It's a great pleasure, great honor to be here today to present this work, which is going to deal with some topics that are generally considered heretical, at least in quantum chemistry. Of course, stochastic in this community, coming from computer simulation, is perhaps not so unusual, but non-unitary, which actually leads to non-Hermitian quantum mechanics, is generally considered treacherous, dangerous waters. And what I'm going to show you is that, in fact, things are under rather more control, and that by making these certain transformations, we can dramatically simplify the correlation problem that we face in quantum chemistry. So this is an outline of my talk. I'm going to, first of all, explain why we have to move to non-Hermitian problems and how that helps with the correlation problem. And then secondly, how stochastic approaches can actually help to solve non-Hermitian problems. And then I'll show you some applications to some weakly and strongly correlated systems. And not sure how far I will get on the application side, but let us see. Okay, let's first of all start off with the problem that we would ideally like to solve, which is the many electron Schrodinger equation. It's shown here, and this means that we're working in the clamped nucleus approximation. So we imagine we have a set of nuclei that provide an external field, and we have our n electrons which sort of move around in this field, and we're interested in the ground state or potentially excited states of such a system. And now there are three reasons why this problem, as it's presented, is very, very difficult. And the first reason is that we're dealing with a problem with very high dimensionality. So even a medium-sized molecule will have 30, 40, 50 electrons. Of course, large ones will have many more electrons. And the object that we're interested in is this wave function, which is a function of the coordinates of all of these electrons. And there are very few subjects where the explicit object that you're trying to calculate is a very high dimensionality object with hundreds of dimensions. That's the first problem. So in principle, the information content, if you like, in such a many electron wave function is simply gigantic. Now, the second problem is that these variables that we're dealing with, these are electronic coordinates, these are continuous variables. This means that electrons can be anywhere in space. Okay? And so the problem is, of course, in that sense, a partial differential equation. And it also turns out that some certain features of the wave function means that in principle, we need rather high spatial resolution to be able to account for correlations in the problem. And then last but not least is the fact that we're dealing with fermions, and so we are only interested in fully antisymmetric solutions to the problem. And this means that viewed as from an eigenvalue perspective of the original Schrodinger Hamiltonian, the actual solutions that we're interested in are much, much higher in energy than the ground state solutions that this Hamiltonian would itself admit. And it's the combination of these three problems that leads us to more or less insuperable problem. Okay, now what is done in quantum chemistry is not to directly tackle this problem, but to actually replace it with a subtly different problem. And what is done is that we move from a first quantized description, that is Schrodinger, into a second quantized description. And we do this primarily in order to deal with the fermionic aspect of the problem. So what is done in quantum chemistry is that we introduce a number of what are called spatial orbitals. You can think of these as being atomic orbitals or molecular orbitals, and there are m of them. M will typically be something like the number of electrons times 2 or 3 or 10, 100, something like this. It's a finite number. And associated with each orbital are these fermionic creation and annihilation operators. They're indicated as C, dagger, P, and sigma, sigma being a spin index, alpha or beta, and P running over these M orbitals. And these creation and annihilation operators satisfy the fermionic anti-commutation relations. And what this means is that whenever you apply H to any function that's not fully antisymmetric, it simply kills that component of the function that's not antisymmetric and leaves you just with the antisymmetric component. And so the basis, suitable basis for representing such Hamiltonians are determinants, determinants being the natural antisymmetric objects. And these parameters, H, PQ, and VPQRS are simply the representations of the Schrodinger operators in the basis that we are dealing with. And they, if you like, these parameters, which are m to the 4 of them in general, if you like, define our Hamiltonian now. And in practice, these orbitals are usually given by some mean field calculation, restricted Hartree-Fock, and so on. And these orbitals are delocalized typically over the extent of the molecule or solid that we want to model. Okay, now, what's the problem with this approach? Now, the problem is that when we're dealing with real space, you know that you simply want to keep the electrons apart. Distance is a good measure in real space. However, when you move into orbital representations, you lose this measure. These are simply abstract quantities. And so, whereas correlation as a phenomenon, which is not a specifically quantum phenomenon, incidentally, correlation is simply a statement that there are such things as conditional probabilities. We're used to, in our everyday life, dealing with conditional probabilities. It's not specifically quantum phenomena. I mean, so an example of a correlation is that, you know, if you find yourself in a country where everything is running smoothly and is well oiled and so on, the chances are that you're in Switzerland, you know. You're most definitely not in the UK, let's put it this way. And that is an example of correlation. It's simply an expression of conditional probabilities. On the other hand, once we've moved into this sort of orbital representation, the only way we can introduce correlation is through superpositions of our basis functions. And these superpositions is essentially quantum phenomenon. It's actually quintessentially quantum phenomenon. So we've taken a phenomenon, namely correlation, that was originally nothing quantum about it, and we've made it a deeply quantum phenomenon as a result. And this, I believe, is fundamentally the source of inefficiency that we face later on. So now the number of terms in this sum grows combinatorially. It's shown over there. So as m the number of orbitals grows, or as n the number of electrons grows, the number of terms simply explodes, and explodes very, very rapidly. And that leads you to intractable problems. And as a technical aside, I'll say that most quantum chemistry methods are based on variational principles, where you try to minimize these coefficients, these amplitudes. So you optimize the amplitude so as to minimize the energies. I'll come back to why that is a drawback later on. Okay, now, one problem that is known, and in fact is a rigorous analytical feature of wave functions, is the fact that because you have Coulomb singularities, if two electrons find themselves on top of each other, of course, the energy diverges to plus infinity, but you have a finite energy at the end of the day. And so something has to compensate for that. And what compensates for it is the fact that the wave function develops these cusp-like features at coalescence, and this is a rigorous condition given by the Kato cusp conditions. And the existence of these cusps leads to the fact that when we are doing orbital-based expansions of our wave function, we end up with a very, very slow convergence of the energy. The energy, in fact, converges only as 1 over m, m being the number of orbitals, and remember the cost of the calculation is growing exponentially in m. So this is very, very bad news. Now what's known, and this goes back to the early days of quantum mechanics with Hilarius, is that actually if you want to get an efficient description of electron correlation, then you need to have wave functions that are dependent, at the very least, on distances between electrons. And these sort of what are called explicitly correlated methods in quantum chemistry usually follow the work of Kuzelnig and later on Tenno and so on. But it turns out that these methods actually introduce what are called a first-order cusp condition, where on the right-hand side, where you have the value of the wave function at coalescence, of course the wave function is not known, they replace that with the Hartree-Fock wave function. Now that may be a good solution, good approximation in weakly correlated systems, but in strongly correlated systems where the Hartree-Fock wave function is itself very far from the true solution, it turns out to be a poor approximation. And so these explicit correlation methods in quantum chemistry are usually only applied to weakly correlated systems. Okay, so this now brings us to where we want to go, which is we want to ask the following question, that here we have the wave function psi, and we want to ask, can we write it in a factorized form? E to the tau. Tau is an object, we call it the correlator. It's essentially going to contain our understanding of the pair correlations in the system, multiplied by some unknown function phi that is now going to be the object of our calculation. And for reasons that are going to be clear shortly, I'm going to insist that our correlator tau is a Hermitian operator. Okay. Now, so we now substitute our ansatz into the Schrodinger equation, and we simply rearrange, and we end up with this effective Hamiltonian e to the minus tau h e to the tau. And this is now a new eigenvalue problem for our function phi. It contains the same original eigenvalue as the Schrodinger Hamiltonian, but the wave function is no longer psi, but is in fact phi. And tau is going to be given to us through a different methodology. For example, variational Monte Carlo. So we're going to be presented with a tau, and then we're going to ask, well, what is the corresponding phi as a result? Now notice that this Hamiltonian that we've got over here is no longer a Hermitian Hamiltonian. And that's because our transformation tau was Hermitian. So this e to the minus tau h e to the tau is no longer Hermitian. It's a similarity transformation, but it's a non-unitary similarity transformation. Now you can say, well, actually, I don't like non-Hermitian problems. Suppose I insist that I keep this Hermitian, the resulting effective Hamiltonian Hermitian. Well, you can do that by introducing not tau, but I times tau. And then the corresponding transformation would not be e to the tau, but would be e to the I times tau. That creates you a unitary transformation, and the corresponding Hamiltonian then becomes Hermitian. So why don't we do that? Well, let's see what happens. So let us now expand the effective Hamiltonian by expanding the exponentials and gathering terms, and this is called Baker-Campbell-Hausdorff, and we end up with a new Hamiltonian that I'm going to call H tilde, and that is the original Hamiltonian, H, plus a whole series of terms that have been added, a first commutator of h with tau, second commutator of h with tau, and that series in principle goes on for an infinite number of terms. So that sounds like not a very promising thing to do. We've taken a difficult problem and then we've added an infinite number of terms to it. That doesn't sound very promising. So what is going on here? Now what's going on here is that this first commutator turns out to be an extremely interesting object, because if you choose tau appropriately, then you can actually cancel to a large extent the interactions that occur in the Hamiltonian. And that is something that we'll demonstrate in a second. Now, that, however, requires tau to be a real object. If, on the other hand, I don't have tau here, but I have I times tau, I introduce complex interactions. They kind of rotate me into the complex plane, and I lose this effective cancellation that I otherwise have when I work with a Hermitian real object. And so that is why we're going to insist on this non-unitary form. That commutator is actually is an anti-Hermitian operator, and so the resulting Hamiltonian is non-Hermitian. Okay, well now, you'd say, well, this sounds too good to be true. You've added a term to the Hamiltonian which largely cancels the interaction. So that should in principle lead to a simpler problem. Well, of course, if it's too good to be true, it usually is too good to be true. And that's because we just haven't added this term, but we've added the double commutator, the triple commutator, and so on. And it turns out that these additional terms lead us to higher body interactions. And so then the question now becomes the following, is that are there forms of tau for which simplification occurs? In other words, this first order commutator does its magic, but the second order and higher order commutators are still small, and so we are left with a tractable problem, or does it put the spanner in the works and we lead to intractable problems? And the interesting answer to this question is that in fact there are physically useful forms of the correlation factor that lead to simplification, and that is what I want to show. So there are many questions that arise here, so first of all, does this commutator series terminate? Or is it an infinite sum, which we have to somehow deal with? Can it be resummed in certain cases? Is this similarity transformed Hamiltonian, is it evaluable? Are the terms actually calculable? And it's, of course, non-Hermitian, and is that going to be a problem? Okay, so now we've actually looked at two forms of the correlators, both of which exist in the literature. So, and so that's very useful for us. One form is called the Jastrow form, which is useful in the context of ab initio Hamiltonian, actually starts in first quantization and writes this tau as a pairwise sum of a function u, which is a symmetric function of pairs of electrons. But it's going to be a function that is going to have quite a sophisticated form, so it's not just going to be a function of the distance between the electrons. That is what Hilarius would have told us. But in fact, it's going to involve more sophisticated coordinates. And it turns out that the flexibility that we have in this, what is a six-dimensional function here, tremendously simplifies the eventual solution of the problem that we want to look at. The second form of the correlator is useful in the context of lattice models such as the Hubbard model and is called the Gutzwiller. And if I have time, I'll come also to present work on this second form, but we'll mostly concentrate today on the first form. Okay, so this is what we're going to do. We're going to take our Jastrow form, and it turns out that in this case, that this commutator series for our Hamiltonian truncates rigorously at second order. So you have the first commutator, you have the second commutator, and then you have nothing else. And that turns out that was a fact already known in the 1960s, boys and handy. And it basically comes from the fact that we have a correlator that only depends on electronic coordinates, so all the potential energy terms in the Hamiltonian commute with tau. So the only terms that don't are the kinetic energy terms. But the kinetic energy terms is a one-body second-order differential operator. So when you differentiate the first time, you end up with single differential operators. When you differentiate a second time, you end up with a commutator that is purely a function of spatial variables. And then the third-order commutator vanishes. And so this expression that's shown here is now the full expression for this similarity transformed Hamiltonian. And you can see it contains terms that go as the Laplacian on tau. It's got this term here, which has got the momentum operator. This is going to be responsible for non-hermiticity, but it's a very interesting term. And then you have another term here that goes as the gradient of tau squared. And now we can now dissect this into additional terms in the Hamiltonian that have got two-body and three-body character. And that is shown here. So these k integrals, these are these effective two-body terms, you see have this term that goes as the Laplacian of u. And now that looks like the kinetic energy. So if you choose your u to be linear in the distance between the electrons, this actually now directly cancels the Coulomb singularity. So these terms mean that the phi function no longer has these nasty cusps that the original wave function had. So we remove this nasty non-analytic behavior of the cusp condition. And that then means that we expect our phi function to be much more rapidly convergent with respect to the basis set. So that's one thing. So this is an example where where the first commutator is actually screening, to some extent, the Coulomb interaction in the Hamiltonian. Now that aspect has been well known and well understood. However, there is a second term which is very interesting, which is these terms that involve these gradients. Now these turn out to be the non-Hermitian terms in the Hamiltonian, and they turn out to actually induce compactness into the wave function. So what these non-Hermitian terms do is the following. So non-Hermitian means that the process is no longer symmetric. And it turns out that what it does is that if it takes two electrons that are close to each other, the amplitude to separating them is large. However, two electrons that are far apart from each other, the amplitude to bring them back together is suppressed. And that is the physical basis of this non-Hermitian terms, which, as we'll show, actually leads to much, much simpler eigensolutions for the Schrodinger Hamiltonian. So that's all the good news. But what about the bad news? The bad news is that we have, in addition to the two-body terms, three-body terms that we have now introduced into the Hamiltonian, and they are shown here. And these three-body terms, you have to treat them. You cannot neglect them. In fact, they make an enormous contribution to the energy. So that is the problem that we face. So we've taken a two-body Hamiltonian and we've created a three-body Hamiltonian, which is in some sense more complicated, but in some sense simpler as well. Okay, now all of this was actually known a long time ago. Boys and Handy worked on this in the 1960s, and they actually, when they wrote down this Hamiltonian, then proceeded to solve it within a kind of a variational scheme, which of course, because you have non-Hermitian object, you cannot minimize energies, and this leads you to great difficulties. And in particular, they wrote it in this what's called Slater-Jastrow form, this e to the tau times a single determinant with orbitals that they tried to optimize, and they ran into very serious difficulty. So instead, what we're going to do is we're going to keep our orbitals fixed, and we're going to keep our tau fixed, and instead we're going to look for linear solutions to what is this non-Hermitian eigenvalue problem. And that is going to be expressed in this form. So we have a non-Hermitian problem, which means that we're going to seek right and in principle left eigenvectors. Okay, now one of the things that we then discovered is that the normal process that we use in quantum Monte Carlo, which are projective techniques, not variational techniques, naturally solve this problem that we've just mentioned. And so what we do in quantum Monte Carlo is we do imaginary time propagation, which means we have this propagator, which is essentially e to the minus beta h. H is the original Hamiltonian, and we're interested in solutions in which beta goes to infinity. That gives us the ground state. And so if we start off with some wave function, trial wave function, it can be the Hartree-Fock solution. If you can do this projection, then at long beta, large beta, you actually take the wave function and transform it onto the ground state wave function. That is what is done in imaginary time propagation. Now, the statement here is that we can do exactly the same thing, except that we replace the Hamiltonian with H tilde, the similarity transformed Hamiltonian. And this same process leads us to phi 0. That is to say, the appropriate wave function such that when you multiply it by e to the tau gives you the ground state wave function. And that's a statement. And the proof of this is actually shown here, and is as follows. So let's suppose we have this function psi of beta. This is the wave function at this imaginary time beta, and we can write it in two ways. On the one hand, we write it as e to the tau times phi of beta. This is the object that we want to calculate. And on the other hand, we write it as the normal propagator, e to the minus beta h. This E0 is introduced for normalization purposes, acting on the original initial wave function, psi 0. But this psi 0 we now write as e to the tau times our initial trial wave function, phi 0. And so just rearranging this equation just by multiplying this e to the tau and bringing it onto the right-hand side, we end up with e to the 5 beta is then e to the minus tau. We have our usual propagator, e to the minus beta h, e to the tau, phi 0. And that's what we have. And now we do the same trick as is done normally in path integrals, which is that we invent some large integer, I've called it m over here, such that beta over m is small, and we now decompose the exponential as a product. E to the minus beta over m, that's small. H, the original Hamiltonian. E0 is just therefore normalization, all raised to the power m. So you imagine you now have a long string of products, m of them. In principle, this is now going to infinity. Okay, now let's write this long string out. So that's one of them here. That's another one here, and so on. And now what we're going to do is, in between each of these big brackets, we're going to introduce the identity operator in the form of e to the tau, e to the minus tau. That's what we do here. And we do the next one out here. Now you take this e to the tau and you let it act to the left-hand side, and you take this e to the minus tau and you let it act to the right-hand side, and so on. And you do this for each one of our brackets. And now you see that this 1 remains a 1 because you had an identity operator that you were introducing, and this Hamiltonian now becomes the similarity transformed Hamiltonian. And we can now re-exponentiate it and get it back into the form that we had. And so that is really very interesting, because it means that you don't have to make any change to your program. You simply have to allow for the fact that you have a non-Hermitian Hamiltonian. So the amplitude of going from determinant I to determinant j is now different to going from determinant j to determinant I. But the same process applies when you do this imaginary time propagation. So this is an example of this process. One is if we do it deterministically, which you can do for small systems. Sorry. And the second is if you do it stochastically using the algorithm that we call full CI quantum Monte Carlo, that I will shortly explain. But the main point is that this thing just converges. You don't go to minus infinity or other sort of disasters that you normally have if you try applying variational methods to non-Hermitian problems. That's it. It's completely stable, in other words. Okay, so now we're going to move on to a stochastic solution. And this brings us to the topic of FCI QMC. Now, yesterday we heard a beautiful lecture from Sauro Suchi on lattice Boltzmann and cellular automata and so on. And there's some connection here between the way I view this problem and actually those types of methodologies. Because what you can do is actually view the Schrodinger equation, the eigenvalue problem, which is generally considered in variational form. You can actually view it very differently as a set of kinetic equations. They're actually first-order kinetic equations, where the eigenvalues that you, the eigenvectors that you seek are actually steady-state solutions of what are kinetic processes. And that is the philosophy that I sort of deal with when I'm inventing these Hamiltonians. So that is to view this coupled set of equations as first-order kinetic equations, like driven by a master equation where it's given. The master equation is shown here. Of course, the difference is that whereas normally these CI coefficients, when you're dealing with densities, are always positive objects, here they can be positive or negative objects. And so what we're going to do, and that's what we do in quantum Monte Carlo, is we abandon the notion of amplitudes per se, and instead we introduce entities that are called walkers, that are essentially delta functions. These are objects that we're going to use to sample the space. Because our space is finite, even though it's exponentially large, our walkers are going to be Kronecker deltas, they're not Dirac deltas, so a bit easier to think about. But crucially, our walkers, which are going to reside in our Hilbert space, are signed. They can be +1 or -1. They're signed walkers. They're not always positive. And the hypothesis is that we're going to say that the CI coefficient on any given determinant, that's our element of our Hilbert space, is going to be proportional to the signed number of walkers on a specific determinant. So that is essentially given by this sum. Okay, so this is an example. So if we have a problem here, I've got an example with 11 walkers somehow distributed in my Hilbert space. So that is somehow described by this line here. And so you see I have positive walkers, negative ones, and there are 11 of them. And I should point out that what this number of walkers represents is really a representation of the L1 norm of the wave function, which is different to the way we would normally normalize our wave function, is with respect to the L2 norm. Okay, so what our algorithm is going to be is we're going to view our Schrodinger equation as these kinetic processes where we give rise to birth and death of new walkers, driven by the Hamiltonian. So the birth processes are given by, these are now random processes that are dictated by the off-diagonal matrix elements of the Hamiltonian, the death processes by the diagonal matrix elements of the Hamiltonian. And the key point here is that you have positive and negative walkers. Whenever they encounter each other, they annihilate each other. And that is essential part of the algorithm in order to stabilize the signs that you get. Okay. So let me just show you an example of this method using our latest algorithms and code on a rather non-trivial problem. This is the benzene molecule. Benzene is 30 valence electrons. And this we're going to treat in a standard quantum chemical basis that is called CCP-VDZ. It's got 108 orbitals. And the accessible Hilbert space in this problem is 10 to the 36. So it's an absolutely gigantic problem. And we're going to sample this now with 20 million walkers. And so here we start the calculation off with, I think it was 100 walkers on the Hartree-Fock determinant. That's the energy of the Hartree-Fock determinant. And here, this is as a function of the number of iterations. You see you converge in about 40,000 steps, iterations. And crucially, you have a stable solution. And you can run this calculation on for a year if you wanted to. It would give you this totally stable solution. Would not go anywhere. Okay, that's the energy that we get. Now the question is, how good is this energy? Okay, now, benzene is actually a relatively weakly correlated molecule, and there are very, very efficient, accurate quantum chemistry methods that can treat it. And these are called couple cluster, which you can do at various orders. CCSD is essentially second order. You can go to third order, so the CCSD gives you this energy here. To third order, this is CCSD brackets T, which is generally considered to be the gold standard of quantum chemistry. That gives you the green line. And if you want to go beyond the gold standard, you can take it to fourth order. It's very rarely done, because the cost of these calculations goes up incredibly steeply. So CCSD takes 2 seconds to do. CCSD brackets T, the gold standard, takes only 10 seconds. But when you go to the next order, it jumps to 16 hours. And then if you ask, well, what happens if I want to go to fifth order? Well, the answer is, forget it. You will not be able to run that calculation. Okay, so these are our benchmarks, especially the blue line, but bear in mind it's not exact. The true energy is probably a little bit below that, but we don't know how far below that. Incidentally, it's not only the fact that fifth order would take rather a long time, but actually involves rather a lot of memory, about 20 terabytes, I would estimate. And these quantum chemical methods are not highly parallelizable, so those 20 terabytes had better be, only 5 minutes, had better be on one node. Okay, so this is our original run, and now what we're going to do is we're going to focus on this latter part, and that is actually shown there. You see, that is what we get. We come out a couple of millihartrees below CCSDT brackets Q. Now the question is, what was the cost of this calculation? So I'm now going to show the same thing, but now expressed in CPU time. This is the actual wall clock time that you had to wait, or a poor graduate student has to wait to do the calculation. And this was run on 16 nodes. Each node, I think, had 20 cores. And essentially what you can see is that in only a few hours, you can actually pick up this rather accurate energy. And more to the point is that the memory usage is only 50 megabytes. And this is really the key gain when you do stochastics as opposed to deterministics, is dramatic gain in memory. Okay, now let us go back to our Jastrow factors. And so the form of this correlation factor, so we're going to go back, switch back again. If for U is a form that was actually originally suggested by Boys and Handy, and actually has terms that go as the electron nuclear distance, that's these Ri terms, and terms that go as electron-electron distances, that's Rij terms. And when they're both non-zero, you end up with terms that go as electron-electron nuclear distances. And these parameters that define this Jastrow function, these are these CNML, we simply took from the literature. There's a variational Monte Carlo study by Schmidt and Moskowitz for the first row atoms. So we simply grabbed what they had obtained through VMC. Now, the form of this correlation factor looks a little, let me just go back. Looks a little baroque. You see, you've got these electron-electron nuclear terms. You know, are they really necessary in this correlation factor? Now, when you actually plot the correlation factors, this is what you get. And we plot two forms of them, one that we call SM7, 7-term Schmidt-Moskowitz, and the 17 one. The 7-term one does not include any electron-electron nuclear terms, whereas the 17 one does. And what you can see is that the more sophisticated form leads to the following property. So what we're going to do is you have a nucleus here. We're going to fix one electron at some point, distance Z1 from the nucleus. And then we're going to drag the second electron through it. And what you see in this correlation factor is that as you move the reference electron away from the nucleus, the correlation factor gets deeper. This means that if two electrons are close to a core, a nucleus, so they're core-like, the correlation factor is shallow, whereas when you move them away into the valence region, the correlation factor becomes deep. And this is because they're becoming more strongly correlated. And this form, this 17-term form, gives you that flexibility. Okay, so this we now take our similarity transformed Hamiltonian and express it now in second quantized form. It's shown here. So these first two terms are the usual Schrodinger operators, and these second two terms, these KPQRS, and these terms here are the additional two-body and three-body terms. And this, I'm afraid, is the Hamiltonian that we really have to deal with here. It's a much nicer Hamiltonian, it's smoother, it doesn't admit these nasty non-analytic properties that the original Schrodinger Hamiltonian does, but it does have these three-body terms in it. So how does it actually work? So what we've done here is apply it first of all to the first row atoms for different quantum chemical basis sets, and these are the total energies that we get. I know nobody likes looking at numbers, so let's just plot the results out. So what we've shown is now, first of all, the error in the total energies with respect to what is the absolute state of the art in quantum chemistry. It's called UCCSD brackets T hyphen F12 star. That's what it is. And that's what you get for the total energies, and how the error goes to the exact value as a function of increasing the basis set size from double zeta to quadruple zeta. So that's roughly from about 14 functions to 54 functions in the basis set. And what we have are the results that we get for two different forms of our correlation factor, the 7-term and the 17-term Schmidt-Moskowitz form, the 17-term containing these additional electron-electron nuclear terms. And you can see that essentially, by the time you get to quadruple zeta, we are absolutely nearly exact with respect to the basis set limit of the original Schrodinger equation. Now, when you look at the numbers, you say, well, what are these terms doing, these additional terms? It turns out that the non-Hermitian terms are very, very negative. And in fact, when you just include the non-Hermitian terms, you go well below the true energy by something like 100 millihartries. Then the three-body terms, which are Hermitian, bring you back up, in this case, by about 100 millihartries or so. And this very delicate balancing act between these two terms then leads to extremely precise values of the energy. Now you can say, well, total energies, nobody really cares about total energies. What about something physically measurable like ionization potentials? Well, even in the ionization potentials, it turns out that we once again beat these state-of-the-art quantum chemistry methods. This is UCCSD brackets T. So this is the errors in the ionization potentials. And you can see even at quadruple zeta, we are still somewhat little bit shy of what is called chemical accuracy, 1 kcal per mole. And actually, we are essentially already there with our 17-term Schmidt-Moskowitz already at triple zeta. So I think I'm out of time. So I will now skip about half my talk. And I was going to talk about the Hubbard model, but there isn't any time. But I do want to come to going back. Okay, conclusions and future perspectives. First of all, this non-unitarily transformed effective Hamiltonian is an excellent starting point for second quantization, unlike the original Schrodinger Hamiltonian, which still contains very nasty terms in it. And so what we think is that you do this transformation, and then you second quantize, and then you deal with the fact that you have a non-Hermitian problem to deal with. This Hamiltonian leads to both fast basis set and also CI convergence. That's what I wanted to show you in the Hubbard model, but there is no time. And full CIQMC turns out to be a good projective solver, and it could handle the three-body terms efficiently. So normally the three-body terms are total pain in the neck, but with the stochastic sampling, it turns out to be good. And our experience with the Hubbard model shows, although I didn't go to it, is that this will be a good method for strong correlation. And incidentally, I should point out that dispersion interactions are also relatively easily treated through our Jastrow factor. And I will finish just show you my group. Honjong Luo, which is actually here, has really been instrumental in helping me develop this. Honjong is actually a mathematician, a real mathematician, and he sort of helped me, chart these treacherous waters that have these non-Hermitian problems in them. So I shall take your questions.
Thank you, Ali, for the beautiful lecture. Please here.
Well, atoms are not very fascinated for quantum chemists, right? So I suggest, have you considered to reproduce actually the complete basis set limit of potential energy dissociation curves? We have examples, for example, for F2, CO, N2, right?
Sure. Those are on the way.
Because when you have all kinds of correlation effect, short range, medium range, long range dynamic correlation, and also non-dynamic correlation.
Yeah, but the point is that here the Jastrow factors largely take care of the dynamic correlation. The CI expansion takes care of the non-dynamic correlation. So that's actually not a problem at all.
No. I don't think so, because in dissociation limit you have different type of correlation.
Correct, yeah.
Because of high spin fragments, something like that.
Sure.
This is difficult problem, right?
As I say, I don't think that's going to be a problem.
Okay.
But, yeah.
Okay, we will see. Okay, so you are going to do this, right?
Yeah, absolutely.
Thank you.
Here. No, there. Here. Look at me.
Thank you, Ali, for this beautiful lecture. My question is about, this resembles a lot to the importance sampling that we do in QMC, in standard QMC. And I would like to understand better what you think about that, because it's like if you are now, you did all this work to work in the basis of determinants, but now you are going back to, well, you have more than one determinant, you have millions of determinants, but putting the correlation inside with this Jastrow factor and three-body terms, this is something that we do also.
Yeah, no, absolutely. But you see, the point is this, that, I mean, within a basis set approach, you have very slow convergence, usually, because of this cusp features. So the point is that when you take care of that analytically via the Jastrow factor, you end up with a much smoother Hamiltonian. And that then means that if you now go back to your basis set approach, you end up with much more rapid convergence. Was really the principal aim here. But of course, the other thing is that our CI expansion for the phi function is completely flexible. So we do not impose any nodal constraints that you otherwise do in fixed node DMC. So this is why I think that we get, if you like, best of both worlds.
Just another little question about excited states. Can you do excited states?
Yeah, the answer is, for the Hubbard model, we've looked at excited states and we can do them. But they are more tricky in non-Hermitian problems because they don't form an orthogonal set in general. And, but we think that you have to calculate the left eigenvectors and proceed like that. So there are some trickiness there, but I think it's doable, yeah.
Thank you, Ali. A really important problem where you get non-Hermitian Hamiltonians is, of course, the treatment of metastable resonance states.
Indeed.
Have you tried using these types of techniques?
Not yet, no.
Because this would be a beautiful thing to do.
Yeah, no,
right?
I agree. But I mean, what I'm showing you is work that's from the past 6 months or so. Yeah.
Somewhere on the right. Who raised? Okay. There.
Thanks. Thank you, Ali. That was really nice. As you were flipping through the last slides that you didn't get to talk about, I saw one that went by very fast. It said real-time propagation, and I want to open the door on that for you to say just a couple of words about. So how do you think this goes over to the real-time?
Okay, hang on.
realm.
So we have done real-time propagation,
You have.
but with respect to the original Hamiltonian, not the similarity transform. In principle, because the similarity transformation doesn't change the spectrum of the Hamiltonian, in principle, we should be able to also do real-time with this H tilde rather than the original Hamiltonian. But we haven't gone in that direction as yet. As regards the real-time problem with the original Schrodinger Hamiltonian, yes, that is doable, but you have to generalize the algorithm to second order in time. It turns out that if you just do first order propagation, you very rapidly move. So when you're doing real time, of course, you're performing a unitary transformation. If you propagate only to first order in time, you can show that you dramatically violate non-conservation of the unitary norm. But if you do it at second order, and unfortunately we only figured out a non-symplectic second order algorithm. I haven't been able to figure out a stable symplectic one. I can talk to you about that. But it turns out that that is then very stable. And you, of course, you have complex walkers, so you have imaginary plus and minus walkers. And you don't get any particle death, you don't get any Walker death, but they kind of rotate round a clock. So you spawn a child, and then your grandchild comes back and kills you. So you get some really funky stuff going on there. But it turns out to be stable. And so we can actually so we've done some photoelectron spectroscopy with this, but with the original Schrodinger Hamiltonian, with all of the attendant problems, with lack of basis set convergence, and so on. But yes, so I think there is possibilities there, and I have one very good PhD student who's been working on it. But it's a bit of a side project for us, but potentially it's a very interesting one.
Okay, I take the privilege of chairing the session for asking maybe the last question, if there aren't any others. So concerning this observation you made according to the non-suitability of variational approaches to non-Hermitian problems, it seems to me that it's not quite Hermiticity or not, but the boundedness of the spectrum, which has to be bounded from below to apply a variational principle. But this is exactly the same condition that you require for your imaginary time propagation not to explode. So it seems to me that what you need for propagating the wave function is exactly what you need for doing a variational approach.
Well, I don't know. I mean, usually when you do variational, is you simply try to minimize the energy.
If the spectrum is bounded from below, you will end up to the ground state, right?
Well, okay. I mean, people have really tried this, and they failed with this.
Why?
Hamilton. I don't know why.
Okay.
I mean, so what I'm saying is that this has been multiply tried. Boys and Handy tried it in '67, and then it was tried several times. And this is actually why it was abandoned, actually, as a way of doing.
But I would say that by the same token, you should fail as well, but you don't.
No, but we don't fail. That's because at no point, you see, we just do pure projection. We don't ever appeal to a minimization principle.
Yes, but if the spectrum was not bounded from below, you would fail. If you don't fail, it is that it is not bounded from below, and then variation should work. But
No. So this is okay. This is we have to discuss.
Okay.
I mean, our proof shows that if you do imaginary time, this imaginary time dynamics, you smoothly converge onto.
These I easily buy, but this, in my understanding, would imply that variation should work as well. But
No. But in general, if you have a non-Hermitian Hamiltonian, a finite one, you've got a bounded spectrum, but you cannot apply variational techniques to this.
Okay.
Yeah.
No other questions? If not, it's time to thank again Ali and to refresh ourselves with a coffee. Oh, sure.
Yes, before we go to the coffee, there is always the couple of announcements at the beginning of the day. Today is not an exception. For the parallel sessions, there are 2 last-minute changes. For the lectures in the Orsay room, the second talk by Maria Celia Righi, she cannot make it, and then the talk will stay, but it will be delivered by Mauro Ferrario. And in the room Lyon, the last of the contributed talks by Robinson Cortez Huerta. Unfortunately, he had a family problem, and he will not be today with us, so that last talk is cancelled. Okay, so now can go to the coffee.